Okay, when after we finish up our kinetics and kinematics part, right now we are gonna have knowledge of vibration, which is gonna be our last subject. This subject is a little bit different than others, so I need to write it down, all this theory behind it, and we are gonna set up the equation one by one. Let's start with the equation of motion, which we use mostly in this course, in dynamic course. Equation of motion, if you remember, is the total force is equal to the mass multiplied by acceleration of an object, which can be shown mass multiplied by the position's double derivative with respect to time, which is x double dot. Let's use instead of this term, let's set up a differential equation of motion of a spring. So we are gonna use an energy method. Energy method. In order to set up our equation of motion for spring, so we know that kinetic energy plus potential energy is constant, which is conserved, right? Constant, let's say. Which is, we know that the kinetic energy of spring is 1 over 2 mass and the velocity square an object, plus potential of a spring is gonna be 1 over 2 the spring constant, which is k, and x square, which is a displacement of a spring, and is equal to, again, we will say constant. Let's take the derivative of both sides. So if we take the derivative, we know that before this one, let's take it out 1 over 2, 1 over 2, okay? So we have m. Instead of v, we know that the velocity is the first derivative of displacement, so x dot square plus k x square is gonna be again constant, multiplied by 2 is gonna be again constant. Let's say again constant. So if you multiply constant with some number, it's gonna be again constant. So it's not changed with time or the displacement. So let's take the derivative of these terms, and if we take the derivative, we will end up m x dot x double dot, right? Plus k x dot, and this is square, right? Let's say it's gonna be 2. Let's say it's gonna be 2 again, because 2 is going down, and then m is constant. X dot, so it's gonna be just 1x, and then inside derivative, which is x double dot, is gonna be the same here. So it's gonna be equal to, if we take both sides, this guy is gonna be 0. So 2 x dot is gone. So it's gonna be m x double dot plus k x is gonna be equal to 0. And Then what can we do? Here we can say x double dot. If I divided each terms with mass, is gonna be k over m x is equal to 0, and in standard form, let's say standard form of this spring motion is gonna be x double dot plus k over m is shown in natural frequency, natural frequency, which is shown as omega n square x is equal to 0. So our differential equation, ordinary differential equation, is this one. Okay. So if we have an ordinary differential equation, which is which order is second order, right? Second order ordinary differential equation. So I'm not gonna go detail, but I will just give you the solution of this kind of equations. Is gonna be if you solve this x double dot plus omega n square x equal to 0 is x, the solution of this x is gonna be a constant a sine omega n t plus b cosine omega n t. So this is the solution of this ordinary differential equation, and depends on the boundary conditions or the initial condition, we can solve this kind of questions, right? There is another way to show this one with phase, which is the solution of this term, this equation, this differential equation is c sine relation omega n t plus phi, which is our phase value, where c, which is this term, is equal to square root a square plus b square, and phi, our phase angle, is arctangent minus 1 b over a. B over a is gonna give us the phase angle, and the constant c is the square root of a square plus b square. The period of this is gonna be 2 pi with our natural frequency Wm, and the frequency f can be calculated as the natural frequency omega n over 2 pi. So this term we need to know, and according to questions we can show the period, we can show the frequency, and we can solve the this question by using the free vibration. This is free vibration equation. Okay, this differential equation is free vibration ordinary differential equation. The next one is forced vibration. All right. In this vibration, let's define first. It is vibration caused by the application of an oscillating force, which is shown by, let's say, F0 or F sine natural frequency with time, or we can describe by the displacement, which is x function, which multiplied by sine natural frequency multiplied by time. So let me plug this guy here, this definition, and let's write our standard form of differential equation. Standard form of ODE, ordinary differential equation of this kind of motion, which is, as you remember, x double dot plus the natural frequency omega, natural frequency omega n square multiplied by the displacement is equal to, if it was free vibration, it was 0. Right now forced vibration, so it's gonna be like F, which is, let's define it like D. 0 is the constant multiplied by sine natural frequency V0 t. So this is gonna be our forced vibration differential equation. If we want to solve this one, I will not go into detail how can we solve this non-homogeneous second order ordinary differential equation. You will go back to your differential equation class and then you will understand how we are solving. I will just write it down. If we have this x function of time, is gonna be the solution of this ordinary differential equation. General solution is a multiplied by sine natural frequencies V0 t plus not V0 here, this is natural frequency, this is the initial frequency, plus b cosine natural frequency multiplied by time, too much by the time, and plus in free vibration we have this solution, but we have non-homogeneous term, so we need to add d0 over natural frequency square minus initial frequency square multiplied by sine initial frequency multiplied by time. So if we can make it in parentheses this term in order to not mixed up. Okay, so we have a solution of forced vibration. If we divide it into, let's define it here, till here is free response. Let me write it down here as, let's write free response. here is this red stuff is free response, like same as before, same as before. It's dice out if there is friction, right? It's free vibration. If there is friction, it's gonna be die out. It means it's gonna fade it. Let's define the other term, which is the second term, which is here. This is the forced response. Forced response. So this dominates. This one dominates. If there is friction. And steady state also. This one. Just let's say, okay, this guy is transient, which is with the time, and this guy is steady state, which means this guy with time is not gonna be like if a long time, so it's gonna be steady state and it's gonna dominate it. Here, if there is friction, it's gonna be same as before, like free, and it's gonna be loses by time, and it's gonna called transient. Okay. For this forced vibration, we have a couple more terms. One of them is magnification factor. It is shown by MF, which is output amplifier amplitude by input amplitude. As we know that from previous lecture, I showed you the amplitude is the height, so it's gonna be x over x0, which is formulated as, let me have a space, 1 over 1 minus the initial frequency over natural frequencies square. So this is magnification factor, how we calculate it. And also we can have the resonance. When we have resonance, when our omega 0 is equal to omega n, which is natural frequency is equal to initial frequency, we have resonance. Okay, we have here, as we said, this is the initial frequency. Let me write it bigger and divide it out, omega n. All right. What happens if we add damping? So adding damping on free vibration. Okay. All right. How we are gonna add damping? Damping means like is your force or your motion is gonna fade it by time. How we are adding damping in the system? We will add the viscous friction. Okay, so it is, let's say, viscous friction for the system. It can be defined as by a force of friction, which is a constant multiplied by x dot, which is the velocity. Okay, if we add a constant, if we avoid this motion, it's gonna be cx dot in the standard form. So our equation of motion in standard form, let's write it down. Equation of motion in standard form for damping, free vibration damping. Okay, it's gonna be what? X double dot plus, so this C is gonna be equal to 2 psi always say natural frequency multiplied by the first derivative of x plus natural frequency square x is equal to 0. Why? Because it's free vibration. So it's gonna be homogeneous differential equation. So this 1 and 2, these terms is free vibration. If we add damping, we need to add in this term. Okay. So let's define our psi is equal to basically C over 2 square root of mass multiplied by spring constant. Okay. We don't need to know right now why this one coming, why it's here, because it's a little bit detailed. So we don't have too much time. So I just briefly showing how we are set up our ordinary differential equation and what is this term. I will just give you the formulation, not the details of this, because all of them has meaning and proof. Interest reader can go to a vibration book and can read it how it can be right. So we have different kind of damping. The first one is critical damping. Critical damping, which is this psi is equal to 1. So you just need to plug 1 and we can solve it. Okay, so it's gonna be x double dot plus 2 natural frequency x dot plus omega n square x is equal to 0. And our this C, this friction force for the critical one is gonna be equal to 2m square root of k m, which is equal to 2m natural frequency for mass spring damper. And what else we can cover? We can cover if it is the solutions for overdamped, which is when psi is gonna be bigger than 1. If it is critical damped, which is as we said, like psi is equal to 1. And if it is underdamped, which is psi smaller than 1, let's define it overdamped. Okay, and let's say critically damped, and we can say underdamped. Okay, let's plug here, and then let's write it down. If overdamped, we said psi is gonna be bigger than 1. Is critically damped, psi is gonna be 1. Is underdamped, psi is gonna be smaller than 1. If it is overdamped, our X solution is A multiplied by exponential lambda 1 t plus B exponential lambda 2 t. So what is lambda 1 and lambda 2? Let me give this one too. Lambda 1 is equal to 2 natural frequency multiplied by square root psi square minus 1 close the square root, and minus 1 is gonna be our lambda 1, and lambda 2 is gonna be minus 2 natural frequency square root of psi square minus 1 close the square root plus psi. Okay, psi. This one also minus psi, and this is minus psi, and this is plus psi. Okay, so this is lambda 1, lambda 2. When you plug here, you will find overdamped. If it is critically damped, so our X values is equal to A plus B T multiplied by time exponential minus natural frequency multiplied by time. So this is when we have critically damped, and the last one underdamped, which is most common one. This one is the most common we see in the nature, and let's depict. We need to pay more attention on this underdamped. So when we have underdamped, as we said, the psi is smaller than 1, and we have most common in nature. And the solution of this underdamped is X is equal to D multiplied by exponential minus natural frequency multiplied by time sine omega dt plus phi. Okay, in this closed loop, if it is if we can want to write a longer format, is gonna be a multiplied by exponential minus psi natural frequency multiplied by time sine omega damping frequency multiplied by time plus b exponential minus psi natural frequency multiplied by time cosine damping frequency multiplied by time is gonna give us the underdamped is not dampened, is underdamped. I went wrong. Underdamped solution, right? Vibration solution. So if you want to find the x, which is the displacement, we can find it. If you find the velocity, we need to take the first derivative of this one. If we want to find the acceleration, we are gonna take the second derivative. Then we can put the vibration force with, if you multiply by the mass. Okay. We use here damped natural frequency. So let's define it. Like, what is this one? Damped natural frequency, and I'm gonna write it as this one, WD or omega D, sorry, omega D is equal to natural frequency multiplied by square root of 1 minus psi square. This is gonna give us damped natural frequency. And we have another definition, which is period of damped vibration, period of damped vibration. Okay, and this is gonna be tau damped, or the period of damped, is equal to 2 pi over, as you guess, the damp frequency is gonna give us damped vibration period. Let's see on this guy. Anyways, okay. Let me delete this guy. Okay. All right. Let me expand. So this is how this motion. I mean, like, we have a long term, then there is a damping. Okay. So it's slowly damping, and then it's fading away. So this is how we are gonna solve our, as you see, our motion with damped the motion, right? We can find x, where is like a time, which time, and then where in this location what is the amplitude, and then what is the location we can find with using this formula. As you remember, we used here underdamped equation, x is equal to d exponential minus natural frequency multiplied by time sine the damping natural frequency multiplied by time and a phase angle. The same thing here. So we have the force acting on it, and then our wave slowly is damping and then fading away. Okay, what is next? The next is if we have again if we add the system adding damping but in forced vibration, not free anymore, simply we are gonna write it down. Our standard form of equation is gonna be mass multiplied by x double dot plus c x dot, right, plus kx, or we can divide it by m everyone, and we are gonna find the natural frequency here, psi here, and blah blah. Is gonna be equal to, in free is gonna be 0, but here is force, so it's gonna be f0 sine omega 0 t. Shortly, in steady state solution, after damping has decreased free response to 0, we will say our x is gonna be equal to x prime sine omega 0 t minus phi prime, and here x prime is equal to d0 over square root natural frequency square minus initial frequency square over both of their square plus in the bracket of 2 natural frequency multiplied by the initial frequency and both of their square is gonna be divided by d0. Okay, this is our x prime, and if we want to calculate the phi prime, is gonna be tangent arctangent tangent minus 1 over 2 2 psi 2 psi omega 0 omega n over omega n square minus omega 0 square. This is minus. Okay, so this is gonna be okay. Here also 2, we wrote it 2 psi omega n omega 0. Okay, and so you just need to write it down, this phi prime and x prime into this form, and you will have the solution of this force damped ordinary differential equation. And lastly, we can calculate our magnification factor as mf is equal to x prime over x0, which is 1 over square root in the parentheses of 1 minus in again parentheses omega 0 over omega n square plus, then we have a space, so, and then in the parentheses of 2 psi in the parentheses of omega 0 over omega n in this parenthesis square. This is gonna be our magnification factor. As an illustration, let me have a space. Okay, so this is how we are gonna have forced vibration, and with damping is gonna be straight when you increase the friction damping. When you add from, look, as you see, 0 to 100 is gonna be flat and it's gonna be faded. So it's complex form. This term is a complex form. So like we just need to concentrate on like how we are gonna, if we have a vibration, how we are affecting. It's just introduction, so you guys are in sophomore class, so not too much detail. I will solve next week couple example in order to have more idea. So maybe I will solve like maybe 1 or 2 questions, and I am gonna finish up. So I will show you like how you are adding each other and then calculate by using this simple formulation, and we will finish up. All right.